Very good morning to all of you. Today we will discuss about beta decay. It is a spontaneous process in which mass number of a nucleus remain invariant, whereas atomic number changes by plus minus 1. As beta decay has three types. Number one, electron emission, or we can say it as beta negative decay. Number two, positron emission, or beta plus decay. Number three, electron capture. In these two, electron emission and positron emission. Electron emission in which there is emission of electron. Electron has negative charge, that's why A is beta negative decay. In positron emission, there is a positron emission, which is the antiparticle of electron. That's why as it has positive charge, that's why we have positive sign here. Now we will discuss. We will study here beta particle energy distribution, for which a setup is used which is known as beta particle spectrometer, which will help in finding out the energy of beta particle. In this we will use a radioactive substance, magnetic field, radioactive substance and magnetic field, and GM tube. Magnetic field is used because magnetic field will make electrons flow into a circular path. After that, this electron will be counted or detected by a GM tube. And why these electrons make a circular path? Because as magnetic field is used, this provide a circular path which is centripetal force. As we know, Fm is magnetic field, Q V cross B, or in magnitude form Fm is equal to E V B, and this magnetic field provide a circular path. It means F centripetal M V square by R. When we equate these two equations, we will get result V is equal to B E R divided by M. It means when we keep this magnetic field as a constant quantity, we see here that V is directly proportional to R. Means if R vary, velocity will vary. If velocity will vary, then the kinetic energy of electron, that will be 1 by 2 mv square, will vary. It means we have a varying energy distribution. When we see the curve of this beta particle energy distribution, we see this kind of curve. Here energy of beta particle, here number of beta particle. This is a continuous curve. It means the particle will carry all the energy in between this range. Now the question here is why the electron, as all the electrons are of same nature, then why there is a continuous curve of energy, means varying energy values. Why this is so? Now is that here is a particle. Now we come to neutrino. Neutrino hypothesis. Neutrino hypothesis. What this theory says? What does this theory say? When there is a beta decay, then with the emission of electron, a particle is emitted, which is neutrino particle. In case of beta negative decay, anti-neutrino particle is emitted, means N plus E minus. When neutron convert into proton, plus electron plus anti-neutrino, it is beta negative decay. In case of beta positive decay, proton convert into neutron plus electron, positron, plus neutrino. This particle neutrino, anti-neutrino, this particle is neutrino. And so when there is emission of electron or positron, then a particle is emitted, which is positron and electron. Then the energy is shared in beta decay, and the disintegration energy is shared between the disintegration energy is shared between electron. If we have case of beta negative, or if we have case of beta positive, anti-neutrino or recoiling nucleus. It means as we were up to that the energy was shared between electrons and recoiling nucleus, but we have unexpected curve, which is continuous curve, which shows that there is a varying value of energies. So neutrino hypothesis theory came, which says that the energy is shared between neutrino recoiling nucleus and electron or positron. As if for example, if we take, according to analytical approach, it was found that the disintegration energy is shared between neutrino particle and the electron. For example, if we take if we have total amount of energy is equal to 10 MeV. If the electron emitted electron 2 MeV energy, then the remaining energy will be carried out by the neutrino particle, sorry, antineutrino particle, that will be 8 MeV is equal to 10 MeV. If the particle, if the electron take 3 MeV, it will be 7 MeV. If it is 4.6 MeV, then neutrino particle will carry out to 5.4 MeV, that will be equal to 10 MeV. So here we see that because energy is shared by these two particles, antineutrino and electron, here we see that the electron has the same nature. All the electrons have same nature, but the energy is varying here. Like here it is 2 MeV, here 3 MeV, 4.6 MeV. So the unexpected behavior of the curve, that is continuous curve, is just because energy is shared by the electron and the antineutrino particle. Now here is energy. Here is total number of particles. Here is end point energy. Endpoint energy. This is the energy, maximum energy of electron. So the unexpected behavior of this continuous curve in case of beta decay can be explained by neutrino hypothesis. Here along this x-axis we take energy of beta particle. Here number of beta particle. It means if we have total energy range 10 MeV, so we can take 2 MeV, 3 MeV, as we have taken the example 4.6 MeV, and so on. When we see at this point, here it is end point energy. It is the maximum energy possessed by the beta particle when the almost negligible amount of energy shared by the neutrino particle. Now we study about the concept of direct reaction and compound reaction. As we have already discussed about the various type of nuclear reaction, now we are left with direct reactions and compound nuclear reactions. Now see direct reaction. As we know, a nuclear reaction is written as X plus A, Y plus B. This is the parent nuclei, this is the daughter nuclei, this is the projectile, and this one is the outgoing particle. When this projectile is incident on this target nuclei, then after nuclear reaction we have a daughter nuclei and a outgoing particle. So direct reaction is energy of incident particle is very high, and it immediately pick up a number of nucleons from the target particle, and the outgoing particle and a daughter nuclei is left out. But in compound nucleus, for example of direct nucleus, direct nuclear reaction is like nitrogen nuclei, that is target, proton, that is incident particle, and it is carbon nuclei, which is daughter nuclei, and it is helium particle, which is outgoing particle, Now we study the compound nucleus. This type of reaction is carried out when the incident particle has a very low amount of energy. In this case, when incident particle is incident on this target nuclei, a intermediate state is formed, that is C star, that is compound nucleus, and this nucleus is in the excited state. After some time, as it is unstable nuclei which is in higher excited state, then after some time it will decay into a final product, that is Y plus B outgoing particle and daughter nuclei. And the momentum of the compound nucleus is same as that of momentum of projectile. Projectile height is x, and because this target particle is at rest, so VA will be 0. So Vx is the momentum of this projectile, will be equal to mcvc. It means the momentum of this compound nucleus will be equal to momentum of this projectile. Then the condition for a compound nucleus is that we should have a minimum amount of energy that is called threshold energy. It is applied in the form of applied in the form of kinetic energy of incident particle plus kinetic energy of this compound nucleus. That will be 1/2 mcvc square, and this energy is applied in the form of kinetic energy of incident particle. So the total amount of energy for carrying out this nuclear reaction will be minus q plus 1/2 mcvc square. This energy is called threshold energy.